Hello, welcome to the fourth and final podcast of week 5. This one's going to be significantly shorter. I just want to touch on a couple theory things that we're going to be actually going into a decent amount more detail later. Now, this first one is from the perspective of what if an acid or a base spills? How do we deal with it? Well, ultimately, it is the H plus, which we now know is actually hydronium ions that can potentially do the damage, and the hydroxide ions that do the damage. So if we can reduce the concentration, if we can lower the concentration of those, then ultimately they're not as harmful. And this is pretty simple. The word dilute literally means, and you know this, think about the dilution equation that we did. Dilute means add some water. That's all it is. And if you add the water, you reduce the concentration, which means you minimize the harmful effects. Now, that's not a perfect solution. It will minimize, but the hydronium and the hydroxide are still present. A method which will actually get rid of the hydronium and hydroxide is a neutralization. And this is the one that we'll focus more on a little bit more in the last unit. But ultimately, if you take a weak base, because we don't want to introduce a strong base into the environment, but a weak base like, say, baking soda, for example, that's that NaHCO3, by the way, that was in that very first lab investigation. Okay, and if you add that to your acid, you can do the opposite as well. You could add a weak acid like, hey, vinegar, which is acetic acid, to your base. And by doing that, you get a harmless ionic compound, and it's a particular type of ionic compound called a salt. That doesn't automatically mean classic table salt, sodium chloride. It simply means an ionic compound that is easy to dissolve. All right, we'll have that, and yay, neutral water. Life's good. Now, check out the formula, or rather the chemical equation for this to happen. Things that you should know is that if you take any acid and react it with any base, strong or weak, you will get the equivalent of a salt. And again, this salt is simply a soluble ionic compound. And you will also get wonderful water. Okay, here's an example of neutralization. If you look below, we're taking nitric acid, and nitric acid, if you think back, is a strong acid, right? It's on our list of 6. And we're going to react this one with sodium hydroxide, which is actually a strong base too. Whew. So ideally, you wouldn't use sodium hydroxide to neutralize a strong acid. Most of you probably don't have sodium hydroxide just hanging around your house, right? Now, this is honestly a double replacement reaction. You were introduced those in Science 10. Like I said, we will talk much more about this in the next unit. I don't expect you to do any questions like this yet. But ultimately, we end up with the cations switching places and the anions switching places, which means now the sodium anion is with nitrate, so we get sodium nitrate, and we have hydrogen combining with hydroxide. Lo and behold, that makes water, right? Remember what I've said about water. Water is just HOH written in another way, so you can see how it all works out. Dun, da, 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 neutralization. Okay, last little concept that I want to talk about before we're done this week is just another clarification about the pH scale. We are going to talk a ton more about pH next week. It's a huge focus, and we get to do some fun new calculations and new formulas that will be new to you. But ultimately, for a very simple overview of pH, it's a way to communicate how acidic or how basic a solution is. Now, the technical definition is you're measuring the concentration of hydronium ions, and that'll make a little more sense when we get into next week's work. But ultimately, focus on what you know to review. pH scale goes from 0 to 14. Oh, yeah, that's familiar. Now, could you actually get a pH less than 0 or a pH greater than 14? Yeah, it is possible. You can imagine a pH less than 0 is incredibly acidic, and a pH greater than 14 is incredibly basic. Now, this table you don't have in your notes, but it's just reminding you about a few of the different substances that are highly acidic or highly basic. And take note here, that hydrochloric acid is right down there. Super strong acid. Oh yeah, super low pH. And vice versa. Look at the top. That super strong base, sodium hydroxide, is right at the top. Oh yeah, these are strong guys. Okay, now how do you know if something is neutral, acidic, or basic? Nothing new. Like I said, this is review, but we would be negligent to talk about acids and bases without referencing pH. If you are exactly at 7, only at 7, like 7.0, that is technically neutral. Okay, so that means not that there is no hydronium and not that there's no hydroxide, but simply that the amounts of each one are balanced, right? They're balanced out. As soon as you start to roll to the left to pH is less than 7, we have an acidic solution, okay? Now, if you go the other way, as soon as you go over 7, then you're dealing with your basic solution. Again, review, nothing new, but man, you got to have this straight in your head, please, guys. Okay, important for you to know, important for us to recap. In terms of how do we measure pH, well, in the labs that you would have done with me this week, we would have used something really simple, just litmus paper, or we would have used pH paper, but there's a huge number of acid-base indicators. We do a lot with acid-base indicators in Chemistry 30. We also usually do a lab in Chem 20 where you get to play with the colors of them. They're really quite pretty because the spectrum of color is beautiful. Now, ultimately, pH indicators are always about, or acid-base indicators, color changes, right? That's the key. We can also do something a little more specific with something called a pH meter. And again, we use these in Chemistry 30. pH meters will actually give you a number value. So for instance, you would put the pH meter, which is a little probe, into the solution and it would come out saying 4.2 or something like that. It's incredibly precise and really, really quite useful. Now, don't get me wrong, indicators that are color changers are helpful. pH meters, though, from an accuracy perspective, are bar none. They're really good. Last thing I want you to do before you get into the assignment and the last question there is make sure you watch the video that I put up there at the end of the notes. I give you a username and password that you need to access these twig videos. It's a good one. It just recaps strong and weak acids. It goes over pH a little bit, shows you some of the indicator colors, and I want you to have that visual of those colors in your head before you try to do number 7, which is another lab investigation. Having a visual of those colors will help you to imagine what actually would be happening in the lab setting. Purpose of the investigation is based upon empirical evidence. Empirical evidence means from experimentation. You are going to have to try to identify unknown solutions as being strong or weak acids or strong or weak bases or neutral substances. Okay, so analysis of data. All right, guys, that's it for me. Remember, if you are listening to this before Thursday, that I will do that Google Meet opportunity for questions at 10 o'clock in the morning on Thursday. You'll have to check the Google Classroom in terms of how to access that Google Meet. All right, talk to y'all later. Bye.